Firstly, it is essential to make sure that the VAR model does not suffer from autocorrelation. If we observe that the residuals are autocorrelated, we must increase the number of lags in the VAR model. In the Canada dataset example from the other tutorials, we estimated a VAR2 model. If the residuals from that VAR model are autocorrelated, we will have to increase the lag length beyond 2. To test for autocorrelation in Stata, we can use the VAR LMAR command to apply the LM test. The null hypothesis of the test states that there is no autocorrelation at that lag order. We also have to specify the maximum number of lags to consider for autocorrelation. There is a lot of debate on how to correctly specify the maximum number of lags. It generally depends on the sample size, type of data, and analysis. In our Canada example, we have quarterly data with 84 observations, and Stata uses the LM test to check for autocorrelation. So, we can consider specifying 4 or 8 in the M-lag option as they are multiples of the length of the seasonal period. Moreover, we are not too concerned about higher lags than 8 in this example because lags from more than 2 years ago may not be as important. In R, we can apply the tests of autocorrelation using the serial.test command from the vars package. In the command shown here, var2 contains the results of the VAR model with 2 lags. The option type allows us to choose among 4 types of tests of autocorrelation. PT asymptotic applies the Portmanteau test and PT adjusted applies the adjusted Portmanteau test for small samples. The BG specification applies Bush-Godfrey LM test, whereas the option ES applies the small sample correction of the LM test. Generally, we prefer the LM tests instead of the Portmanteau tests for VAR models because they have been observed to perform relatively better, especially when the maximum number of lags we are considering is small. However, we have to use the Portmanteau tests in cases where we have to test up to a huge number of lags. This is because more lags consume more degrees of freedom in the LM test and we may not be able to apply the tests. The Portmanteau test performance improves if the maximum lag is sufficiently large compared to the lag length of the VAR model. Moreover, the PT.adjusted should be preferred over the PT.asymptotic option in small samples. The option lags.bg allows us to specify the maximum lag for the LM tests, whereas the lags.pt option is used to specify the maximum lag for the Portmanteau tests. Here, we have applied the LM test using the BG and ES option with 4 and 8 lags because we are testing up to a smaller number of lags. As a result, we are inclined to use the LM type of tests instead of Portmanteau. The results of the Bush-Godfrey test indicate autocorrelation of the residuals. According to this, we should increase the number of lags in our VAR model till the problem of autocorrelation is eliminated. However, the small sample correction using the ES option indicates no autocorrelation. In our case, we may be inclined to use this small sample correction because 84 observations in a VAR model with 4 equations is not exactly a large sample. We can also take a look at the ACF plots of the residuals of all the equations. In the plots, all the autocorrelations at smaller lags are within the confidence intervals, except the RW equation. Even in the RW equation, the autocorrelations at lag 2, 4, and 8 are barely over the confidence intervals. Since we have some mixed results from the autocorrelation tests, we can also rely on other supporting methods. We can estimate a VAR with higher lags and see how it performs as compared to the current model. For example, if our objective is forecasting, then we can use forecasting performance to choose between the lags. Next, let us check the stability of our VAR model using eigenvalues. This test helps us determine whether the variables are stationary and the VAR model is stable. If the VAR model satisfies this eigenvalue stability condition, then the IRFs and FEVDs from the VAR model have a known interpretation. To conduct this test, we have to use the estimated VAR coefficients to construct a companion matrix. The eigenvalues of the companion matrix show us if the VAR model is stable. The stability condition for VAR models states that the moduli of each eigenvalue of the companion matrix must be less than 1. If the modulus of any of the eigenvalues is not less than 1, then the VAR model is unstable. In Stata, the var stable command takes care of everything automatically. This means that it constructs the companion matrix from the VAR coefficients, estimates the eigenvalues, and shows us the results. In R, however, we have to do all these steps manually. That is, we have to obtain the VAR coefficients and construct the companion matrix from those VAR coefficients. Let us see what the companion matrix should look like. The companion matrix is a combination of all the coefficient matrices of the VAR model, identity matrices, and null matrices. In the Canada example, our VAR model has two lags, so it will have two coefficient matrices A1 and A2 for the lags. We have to combine these two coefficient matrices with an identity matrix and a null matrix as shown here. Since we have 4 endogenous variables in the VAR2 model, all these will be 4 by 4 matrices. Our identity and null matrices must also have the same dimensions, which are 4 by 4 in our example. To construct the companion matrix, we append all the coefficient matrices by columns. Then, we append the identity and null matrices by rows and columns as shown here. In our example, we will append the two coefficient matrices A1 and A2 side by side. We will have to append the identity matrix below the first coefficient matrix A1. Moreover, we will have to append the null matrix below the second coefficient matrix A2. Please refer to the R code in the accompanying file to see the construction of the companion matrix in our Canada example. Once we have the companion matrix, we can easily calculate the eigenvalues using the eigenfunction on the companion matrix. Then, we apply the mod function to estimate the moduli of those eigenvalues. The functions applied earlier will give us the eigenvalues and moduli for our VAR2 model as shown here. To interpret the results, we have to consider the VAR stability condition mentioned earlier, which states that moduli of all the eigenvalues of the companion matrix must be less than 1. The results here show that all moduli are strictly less than 1. Therefore, the VAR model satisfies this stability condition. We have no evidence or reason to suggest that the model is unstable. To test whether the residuals from VAR model are normally distributed, the Jarque-Bera test is often used. This test is based on skewness and kurtosis of the residuals. To be normally distributed, a series should have 0 skewness and kurtosis should be 3. Therefore, the skewness, kurtosis, and Jarque-Bera test use this information to test for normality. In VAR, we can apply the Jarque-Bera test to the residuals of each equation one by one. These are known as the univariate Jarque-Bera tests. The null hypothesis of the univariate test is that the residuals for that equation are normally distributed. We can also apply the multivariate Jarque-Bera test, which jointly tests the normality of residuals for all equations in the VAR model. The null hypothesis, in this case, is that all the residuals of K equations have a normal distribution. For skewness tests, we test the null hypothesis that the skewness is 0, which indicates normal distribution. On the other hand, the null hypothesis for the kurtosis test is that the excess kurtosis is 0. If we reject the null hypothesis in any of these tests, it indicates that the residuals may not be normally distributed. In Stata, the var norm command automatically computes and reports the univariate and multivariate Jarque-Bera, skewness, and kurtosis tests. In R, the normality.test command can be used for this purpose. We can specify the option multivariate.only is equal to false to estimate both univariate and multivariate tests. The VAR2 shown here is the object containing the results of the VAR model. If we look at the results of normality tests, we can see that we cannot reject the null hypothesis of all the multivariate tests. This indicates that the residuals are normally distributed. In the case of univariate tests, the residuals of all the equations indicate normality as well. This brings us to another important consideration. The VAR model estimates can still be consistent even if the residuals are not normally distributed. In some cases, we can proceed with the VAR model even if the residuals are not normal. For instance, in some cases, we might be more interested in forecasting performance rather than inference on the coefficients. Thank you for watching, and I will see you in the next tutorial.